Confused.
You're in the right place then. I hope I can help somehow. Well, it's official, folks. Looks like we can get started. Welcome back, everyone. Any questions or comments to start us out today, folks? Okay, well, let's go through our typical announcements.
So like we have an exam next week, but we also have an assignment due on that day.
Yeah, it looks like that's right. So our assignment number 9 is going to be due, no, wait a minute. That one's going to be in April. Let's take a look. Assignment number 8. This one will be due Tuesday, March 12th. So yeah, that's absolutely right.
Okay, thank you.
Other questions? Okay. Well, yep, just as you said, we have our second exam coming up next Tuesday. It's only going to involve these sections right here. So one comment I did want to make about the class, and I'm going to make this official, an actual forum post and put it out there. As far as the due dates go, the due dates right here for, let's say, the assignment number 7, it's more of a benchmark that you have to hit in order to be considered fully caught up for the course. So if you don't have this assignment 7 completely finalized, I will accept it late. In the syllabus, it did say I'm not accepting late work, but it's been kind of a rough semester for several individuals, so I have made some exceptions here and there. So I feel like just for the fairness of the whole course, I will be accepting late work. So let's take a look. That means 7.1 is not on the exam. This is your opportunity to strategize on studying for exam 2. If you decide to leave this one off and not turn it in on the day of the exam, I'd forgive you for that. I'll just assume you were focusing on those sections actually on exam 2. It would mean you have to do additional work to get caught up, to get that assignment turned in, but that would be okay. I would accept it for credit. So our exam is just those sections there. It's going to be, this is the formula sheet I'll have printed. It'll be your last page of the exam. You can tear off it as well if you'd like. So like we mentioned, it's a good idea to familiarize yourself with what's on here before you begin to use it on a real exam. So I would have this loaded up or printed out as you study the sample exam 2 problems or go over your older work and things like that to study for the exam. Other questions so far, folks? Okay, well, it's going to involve just those 3 sections there. If you have questions over the weekend while you're studying or on Monday, please don't hesitate to reach out. I'll be very happy to help. But for the moment, we're now in section 7.1. We're about to complete this section, and I have added another document here called Avoiding Circular Logic. We'll take a look at it in a moment to see what's going on there. And avoiding circular logic, the short of it is we're about to show an identity is actually true, that this is going to be a real equality for all values of theta in the domain of every one of these functions. You'll always have equality here, much like sine squared plus cosine squared is 1. But if we're trying to show that this is true, we're trying to give a literal proof, whether it says verify the identity or prove the identity, we're doing the same thing. And that means the one thing we cannot do is, if we're trying to show that's true, we cannot start by assuming it's true. We'll have more comments about that. So if we can't assume it's true to start, here's what we can do. Let's use a shorthand to say LHS equals left hand side. So that is a shorthand. It means we're referring to this side of the function of the equality. Left-hand side is 1 over sine theta minus sine theta. Likewise, we'll let RHS denote right-hand side. So the right-hand side, we're referring to cotangent times cosine theta. And when it says verify the identity, all we're trying to do is take the left-hand side, show that it's equal to the right-hand side somehow. So your proof is pretty much going to look like this. Left-hand side equals, then you'll do a bunch of algebraic steps. So that's the mystery, that's the work right there. But eventually, keep on putting down equalities, you should get to the right-hand side. If you can do that, if you can connect the left and the right through equalities, taking only valid algebraic steps using the trigonometric identities we're familiar with, then you've done it. You've showed that that's an honest identity, that that equality there holds for all values of theta in the domains. So that's the strategy. But knowing the strategy means, well, there still has to be a lot of interesting things we have to pull inside here. So as you go to solve these problems, good idea to keep in mind that this is pretty much our big sheet of identities. And a lot of these are things we use and take for granted. The bigger set of identities so far in the course are really these three right here. So they'll come up here and there throughout the problems on proving the identities. So let's park it here and just have it available, just in case they come up. Okay, now the next thought you might have is, if you're trying to show the left-hand side equals the right-hand side, or vice versa, going from the right to the left, sometimes what you want to do is pick a side that looks complicated and start simplifying it. Because that's what we're good at, and that's what the notes above were all about, simplifying these kinds of things down. So we've been really practicing to do this kind of problem. In my opinion, I feel like this simplifies easier than that one. So I would probably personally start with the left-hand side. So let's begin the proof now. The left-hand side, I'm just going to copy it in to start. 1 over sine theta minus sine theta. We're going to try to somehow simplify this thing down and make it look like cotangent times cosine. That seems mysterious, but if we were simplifying this alone, probably what we would do is make that a fraction, find the least common denominator, and go from there. So I have a 1 over sine, and then the next operation is this one got promoted to an actual fraction, and we'll multiply this by sine theta over sine theta. That will give us the least common denominator of sine theta down below. Up above, we'll just subtract across numerators. So it's now equal to, let me write in the denominator first, sine theta below. Then across the numerators, it'll be 1 minus. Over here, it's sine theta times sine theta, so sine squared theta. So that's our first step to start out. Any questions, folks, with that adding the two fractions together step? Okay, now that we got to there, let's observe. If you have a sine squared, then you're probably using that Pythagorean identity. But that Pythagorean identity, like we mentioned before, it really comes in 3 different formats. This is the format when you solve for the integer 1. There's a format for when you solve for cosine, and there's a format for when you solve for sine squared. But because it says 1 minus sine squared, here's the thing that we're going to do to that. Let's take cosine squared theta plus sine squared theta equals 1. Let's just subtract sine squared from both sides to get cosine squared theta equals 1 minus sine squared theta. Pretty similar to the problem we did up above in the notes when we started this section. But now I've got 1 minus sine squared, 1 minus sine squared right here. So that's already a substitution we can make. Or maybe blue doesn't make sense. We've already used that up. We're going to substitute this way. 1 minus sine squared, wherever we see it, is a bona fide cosine squared. And we can just insert it right there. So now this is equal to cosine squared of theta divided by sine theta. Now, we're not quite there, but it looks like we're close, right? One thing you want to always take a look at when you're trying to prove an identity is the finish line. I started with the left-hand side. I'm trying to make this function look like that. Well, I have cosine squared, so at least I have that one of these factors of cosine. I'll start separating them out and just see what we're left over with. So down here, if it's cosine squared, that's just as good as cosine theta times cosine theta. The sine theta, I'll just write down under this denominator. And it's starting to actually clear up. we've matched up this portion, so this cosine to cosine works. The only contention is, do we have a cotangent? But we truly do. Cotangent is a cosine divided by a sine. So right by that red dot, that is a cotangent, theta. Then it's multiplied by cosine theta. But that sounds extremely familiar. That's the entire right-hand side. Let's call that RHS. The moment you've done that, the work is done. You can trace the left-hand side through all these equalities and show it does in fact equal the right-hand side. That's what proves identity right here in the middle. Those are true. That's a true equality at that stage. Well, we did it, folks. That's how a proof could go. There's a lot of ways to do these. And I think I've mentioned this comment before. When you're simplifying or proving an identity, there could be as many different ideas and different approaches to this as there are people in the class right now. Some people might find a faster way or a funner way, I could say. But other questions at the moment? Oh, right here. Kind of the idea with that one was, I took the cosine squared, and I first thought of it in this way. Cosine theta, divide by sine theta. So I had a fraction where the numerator got partitioned in this way, just cosine by cosine. But then you could break this up into two fractions. Cosine theta over sine theta times cosine theta over 1. The idea here is in fraction multiplication, we just multiply across the numerators, multiply across the denominators, but also simplify that over 1 and just called it cosine altogether. So it's all a matter of just rewriting, divide sine into the first one, and we get that result right there. Does that make sense on breaking it up that way? Okay. One thing that's weird about verifying an identity is also you have the opportunity to do this weird algebraic stuff that we never really had a reason to do that ever before. In algebra, you usually take this and go in that direction when you multiply the fractions together. But in proving an identity, we want to take something that was already multiplied and undo it as fractions, going back to this stage right here. So definitely wild stuff. Lots of ways to do this one. To me, this is the way how I'd probably think of approaching this one, however. Other questions or comments about it so far?
Just a quick question.
Yeah.
So how did you go from the 1 minus sine squared theta over sine theta to the cosine squared theta over sine?
Oh, this one right here? We took this portion, and the major thought about it was the power of 2 is the bigger hint on it. A power of 2 says you're probably going to be using that identity down below. So we duplicate it over here. And, well, the format of this identity wasn't great because we've got a 1 minus sine squared. And so what we did was subtract sine squared from both sides. So you can fit that in. But now if you have a 1 minus sine squared, that becomes a literal substitution from here down to here, pulling in the cosine squared into that spot. That's definitely tough, right? It's like jumping through multiple hoops to get to one extra equality. Does that make sense on tying that together? Awesome.
First green, that cosine theta over sine theta, that's cotangent by definition.
Yeah, so we just substitute into that position.
What I do, oh, what I want.
Ah, gotcha. Yeah, so this portion, we just literally substituted in a cotangent for that whole fraction. And then the cosine theta, what you could have thought is a cosine theta over 1 when you were first separating out that numerator, just simplifies to that cosine theta. At that moment, we declared victory because that's what our goal had to have been, cotangent times a cosine. But definitely a pretty tricky problem, I'd say. Other questions at the moment? Okay, well, let's talk about this concept once more. It says, do not start by assuming the identity is true. In a way that makes sense, right? If our goal is to show that that equality is true, we can't make our number one step be that equality is true and work from it. And it's almost unfair because sometimes in mathematics, if you're trying to disprove something, you would assume it's true and then get to a contradiction. The contradiction would say, well, that statement was never true in the first place. But for our point of view, we're not trying to prove something, we're trying to show it's true. So the one thing we can't do is circular logic by assuming the truth of that as our first step. If you assumed it's false, I think we would just be stuck because it turns out it's a true statement. So we wouldn't have any algebra to really do at that stage if we make our logical first step that the statement is false. But if we made a statement that the statement is false, you have to come into a contradiction that which disprove the falseness of your original statement. So yeah, if you turn it around like that, it could work. Actually, no, what we did was we started with this, just the left-hand side. Assuming the identity is true would mean we would be using both sides of the statement all at once and worked algebraically on both sides of the equality simultaneously. But actually, you can make that work. You just have to do it in a certain way. What we did was we just grabbed the left-hand side, simplified it in a particular way and showed, yeah, that's the simplified form of the left-hand side. They must now be equal. There's a lot of weird things we can say about these. And honestly, what makes this a difficult topic is it's an honest mathematical proof we're trying to show. And so let's go down to this one, avoiding circular logic. And this is what circular logic would look like in that particular problem. Suppose you did assume the identity is true. Let's ignore a certain part of this for a moment. Assume that that's true. If you did that, it is circular, but you could turn this around and make it work. If you assume that this equation is true, here's what your next step might look like. So assuming equality is true here, let's see, what have I done? Not a lot. I did cotangent and wrote it as cosine over sine. That doesn't seem like too major of a step. Then on the next thing I did here was, let's use the annotate. That might be a little bit more clear. I took this whole left-hand side, multiplied it by sine theta. That means I took the whole right-hand side right here. I wrote it in as cosine times cosine, so now it's a cosine squared, and multiplied by sine theta on the right-hand side and the left-hand side simultaneously. This is confusing, so this is not necessarily the nicest way to prove it. And it's circular logic, it's not the end proof. We have to fix it after we do all this. Let's keep on seeing what happens next. If you multiply by sine theta, then we'll distribute here. That'll turn into a 1. That'll turn into negative sine squared theta. That probably starting to sound familiar in a way. We have 1 minus sine squared theta on the left. Over here, sine and sine cancel, it's just cosine squared. That identity is true right here. In fact, if you add sine squared to both sides, it would look like this. Here's me adding sine squared on the left, adding sine squared on the right. And you get a true statement. 1 equals cosine squared plus sine squared. So it looks like a nice proof in a certain sense, right? But it has one really, really big flaw, which is almost tragic. Sometimes the logic does not reverse the way you want it to. And for this to not be circular, this cannot be your first step. That's what we're meant to show is true. That has to be your first step, and you have to go backwards and show that you can undo every single algebraic operation in this equation to get to the original thing you were trying to show as true. That's even harder in my opinion, but here's what it would look like. This is kind of the optional reading of why it's circular. But if you want to make it a correct approach, you start with what you already know is true, not with what you're trying to show is true. Do some operations. These are the same as the ones above. I just reversed them. If it looks confusing to you, I agree. This is a confusing way to prove it. But it ends on this statement right here, which is what we were meant to show. That's a correct approach. But I recommend doing it this way. In my opinion, especially when you're learning to prove identities, this is way easier. On this approach, I did the right-hand side, cotangent times cosine, then cotangent turns into cosine over sine on that step. Then you can take these, multiply them together to get cosine squared on that step. Here we're using the Pythagorean identity that if cosine squared theta plus sine squared theta is 1, then that would also mean cosine squared theta is 1 minus sine squared theta. And that's what we did right here. Cosine squared theta equals 1 minus sine squared theta. Next thing that happens is I've took the sine theta, divided it here. That's why you have a 1 minus sine theta. It divided here, so that's why the power went down by 1. But that became the left-hand side right at that stage. I think even this method right here is pretty confusing because to make this all work, you have to take something that's already considered pretty simplified and make it more complicated. That's a harder way to go, in my opinion. This is not any easier. Although it's valid, you had to reverse your scratch work right up here to make it work. I think this is honestly probably the clearest way to get through it. Start with something that looks complicated. That's the left-hand side. Combine the fractions, simplify it down until it gets to that simplified form. We're just used to simplifying things. We've done a whole lot of that work in this course and other math work. Usually that approach makes a little bit more sense. Well, any questions at all, folks, on getting through that one? Okay, well, the same comment that I put right here is also duplicated over here in the homework as well. We can't start by proving these identities are actually true. We need to pick a side and just simplify it down until it looks like it becomes the actual other side. If you did assume the identity is true, you might lose some credit on your homework assignment, but I would give you an opportunity to rewrite it. It wouldn't be permanent. But the bigger deal is you would lose credit on an exam problem that we can't rewrite. So we'll always try to harp on this a little bit just to make sure we don't make those kinds of mistakes where it hurts the most, I'd say. And I think what we should do is definitely do at least one more. Does that sound all right to folks? All right, let's go for our next one. Now, I think this one is actually really kind of hard in a way. I'll leave it up to the class. Should we go for this hard one or should we go for kind of a middle ground one before this one? Let's give it a try. Awesome, let's go for it. So what makes this one hard is, well, both sides of this equation don't look very nice to approach. So there's another strategy that we can take. Sometimes you take the left-hand side, you work it out, and you work it out, and you come up with something, which is not the right-hand side. That kind of hurts in a way because it looks like a dead end. It's not necessarily a dead end. If you do this, save that work, and just go to the other position, the right-hand side, simplify it down and simplify it down. You might not hit the left-hand side, but if you come to the same exact expression right here, your work is done. They will link up and your equality will flow this way through the same expression back to the other side. That's what's going to happen on this one. This one's really hard to get the left-hand side directly equal to the right-hand side. But if we can match it up to something, then we're on the right track. So let's give it a try, left-hand side to start. I actually have a cheat sheet for this one in case I lose my way, because this one is kind of nasty. Not a good exam problem for sure, but let's put in cosine phi 1 plus secant phi. And all we're trying to do is simplify this. Now, section 7.1 was about simplifying expressions, and the only real idea we had was try to write things in terms of sines and cosines. Let's take that secant and make it 1 over cosine. We've got cosine phi 1 plus 1 over cosine phi. We made it more complicated with the objective of simplifying it down in the next steps. Now, this is a complex fraction. because in the denominator, the fraction is an additional fraction. But you can clean that up in a pretty fast way. You take that denominator there and multiply this way. Cosine phi over cosine phi. So I'm just multiplying by a literal 1. This avoids the need for adding fractions down there and then multiplying by the reciprocal, which doubles the algebraic steps you would have taken. Here, we're just going to distribute. First, here to here is not so bad. That's just a cosine squared of phi. Now in the denominator, we'll distribute this way. That one's not so bad. Cosine phi times 1 is cosine phi. And then here to here, that's cosine phi times cosine phi for or no, I said that wrong. Maybe it would help if I pointed the arrow in a slightly better way. It's multiplying in this way, going into the numerator. That's cosine phi divided by cosine phi. So that one cancels to a plus 1. Does that make sense to folks to get to that stage? Okay, so we've got cosine squared phi divided by cosine phi plus 1. I mean, I could do some stuff with this. We could write this as cosine squared is a 1 minus sine squared, that same trick as before, but we're going for cosine and a tangent in our end answer. This is the stage where I would feel completely stuck. I don't really know what to do with this. Let's color code it though. There's something we can do at least. And again, a lot of times when people do these problems, they erase all this. The better thing is to actually save it. If I can't get the left-hand side to link up with that, that's okay. We'll just go back to the drawing board and see what happens to the right-hand side. Let's take the same kind of approach. We'll express the right-hand side in terms of sines and cosines, but first let me copy it down so we know where we're starting from. 1 minus cosine phi divided by tangent squared phi. Okay, now the problem can start. I'm going to pretty much redo the same idea that we did over here, simplifying the complex fraction. First, let's copy the numerator, 1 minus cosine phi. Denominator is a tangent squared, but that means it's also a sine squared. A phi divided by a cosine squared of phi. So there's where it sits so far. And it's at this stage where I'd start to get a little unsure where to go from here. But I do think we have some tricks that we can make this work. Let's multiply by the reciprocal of that denominator. We'll need a parenthesis across the numerator if we do that. It'll be 1 minus cosine phi. Multiplied by the reciprocal of this, which turns into cosine squared phi, divide by sine squared phi. Now we're looking at a couple things. I started on the right-hand side, which means I would like to write it this way if I can, but I have a feeling I'm going to get stuck again. But if you can make it look like this step, you've got your proof completed. Notice what we already have. That's already there, the cosine squared. The denominator has to also be cosine, so that suggests what the next step should be. We need to eliminate sine squared in the problem and put only stuff that involves cosine. Let's show the steps up here. If you need to rewrite this so it's in terms of cosine, begin with the Pythagorean identity. Sine squared phi plus cosine squared of phi equals 1. Because of the sine squared there, let's color code it as well, just to show the next substitution. We should solve for sine squared up here and write out that sine squared of phi is 1 minus cosine squared of phi. So that's going to be our substitution for the denominator down here. And let me see if I can zoom just a touch. There we go. So on the next step, let's see how this turns out. It still looks sketchy. I'm not completely sure how this one will resolve. I do have a cheat sheet, so we don't have to second guess it. But this will be 1 minus cosine phi still. I'll leave that cosine squared right where it is. And now in the denominator, where there was a sine squared phi, through the Pythagorean identity, we're putting in 1 minus cosine squared phi. Now, when you look at this, there is no cancellations whatsoever with what we've got. I can't cancel cosine to cosine because of the minuses between them. They're not in a factored form. And I've got to make my denominator look like that, a cosine phi plus 1. There's one additional idea that's going to help us. This is what makes it really kind of a hard problem is I don't think I would have guessed this one right off the bat. Someone gave me this problem and said, solve it in front of a class. I'd probably not succeed on it. This one is kind of hard, but the idea we need goes like this. If you ever have something that looks like an a squared minus a b squared, you have an immediate factorization. You'll get an a plus b times an a minus b. And we, in fact, are looking at that. That's a 1 squared, and that's a cosine squared. So that would factor. Let's do it up here to show how it works carefully using the formula above. 1 minus cosine squared of phi. There's your a squared. That whole thing is your b squared. So a factor is an a plus b times a minus b. Following this format, this turns into 1 plus cosine phi. Then on the next one, this will be 1 minus cosine phi. And that's what's going to go into the denominator here. We're going to just fully factor that out. A good question is, why should we factor that out? But notice there's a 1 minus cosine phi here, and there's 1 right here. We can cancel those things out and hopefully make some progress on the identity. So here's the next step. Down below here, it's 1 minus cosine phi copied in, multiplied by cosine squared phi. Now for the denominator, let's put in our factored form that we did up above the problem. So right here by the red dot, 1 minus cosine squared phi is 1 plus cosine phi times 1 minus cosine phi. This right here is, to me, the major idea of getting through this problem. Any questions at all, folks, to this stage? Okay, well, after all this weird algebra, non-standard kind of algebra you don't necessarily do every day, we're in a good spot because 1 minus cosine phi will cancel. These are factored forms, so the cancellation is now valid at that stage. And notice what leaves over. We now have a cosine squared phi in the numerator divided by a 1 plus cosine phi in the denominator. It looks an awful lot like this one. In fact, they're identical. Doesn't matter if we change the order of addition in the denominator. Addition's commutative. So we just matched up the left-hand side with the right-hand side through this object right here. And just some extra emphasis with the notes, you could call that star, to think of what we were saying right up here. We found the common element. So that means that all of our work is done. This shows that the left-hand side is equal to the right-hand side. This is as worse as it ever gets, but there is one problem in the homework where this could be a pretty valid approach. So again, if you feel like you got stuck, keep your work there and just try the other side. If you keep on getting stuck, take a picture of your work and email it to me. I'll be very happy to take a look at it. I'll use my pen and everything and help you with getting to the next steps. I understand that these are difficult problems, so I'm almost expecting people to reach out and ask questions about how to approach the problems. Well, any questions at all, folks, on getting through that one? Okay, well, we did it. This was a couple difficult trigonometric identities that we needed to solve. Maybe one question for the class. Should we try another one or go to the next section? Your choice today. One
So
more?
like
Okay.
sorry. So we just leave it like there and then not solve until the end. Like what I mean is we just the blue ones.
Yeah, if you leave it like this, then this and this will be telling me that your left-hand side, which equals that blue star, and the right-hand side, which equals that blue star, allows them to link up right here. And so this statement, left-hand side equals right-hand side, is now saying that overall. So you can leave your work just in this format at that stage. In fact, if this is all you gave me, say this was an exam question and you just stopped right here, I would
Mhm.
consider that full credit because you really have shown the left side equals the right side at that stage. This is just an extra statement to emphasize it down below.
Okay, thank you.
Yep, absolutely. Other questions at the moment? Okay, let's go for another one. I have a set of identities that could be fun or could be terrible. So this is our choose our own adventure portion of the class. Oh, some of them have steps. This one says 9 steps. That doesn't sound terribly fun. Let's do one that's not 9 steps. And let's call this one just our part C. If you see something penned in, it just means it's an additional problem that wasn't printed out, put out on the notes. And let's see, this one looks terrible. How about, this one should be pretty approachable. Cotangent theta. Now, there is a really important problem-solving strategy just right here. When you go to solve an identity, you want to make sure you put everything down extremely specifically, because if I make one small mistake transcribing this, it's probably not an identity, and we're going to have a terrible time with this. Don't let that happen to you on your homework. It's horrible miscopying something that's false and try your hardest to show that it's true. So tangent theta below equals cosine squared theta. I would consider this a pretty normal, like a homework question, maybe even an exam question qualify.
Wait, what does the first one say?
I think that was an open mic. But let's take a look at this one and start with left-hand side. Why left-hand side? Because to me, it takes a humongous amount of creativity to turn a cosine squared in a simplified form into that. Not saying you can't do it, but if you can do that, if you could look at this and make it look like that, that's impressive. I'd be extremely amazed on your thought process and getting through that. There are people who can do this. They're impressive. For me, I usually start with what looks complicated and simplify it down. So let's begin with this stage. Cotangent theta. Well, let's just copy it in just to be specific where we're starting. Okay, so there's our entire left-hand side. And now this is where the process starts. Our cotangent, that one's going to be a cosine divided by a sine. So we've got cosine theta divided by sine theta. Then we'll just do it again. Here's another cotangent. So it's cosine theta divided by sine theta again. Then we go plus. And tangent theta, here's our switch. This one's sine theta divided by cosine theta. Well, now it's a humongous mess. We have a very large complex denominator, but the denominators that are interesting are the sine theta, and a cosine theta. When we see those 3 denominators, it would mean that the least common denominator is sine theta times cosine theta. That means if we're going to simplify this fraction in one shot, we should take that least common denominator and multiply like this. Sine theta, cosine theta. Same thing in the denominator, so we're multiplying by 1. We're not damaging equality. And that's going to be our step to approach this one. Let's see how it goes. Okay, so carefully multiplying this out. First thing that happens is you multiply this way. But when you do that multiplication, sine theta, cosine theta is going into the numerator, and it causes a cancellation in this way. It's now just a cosine times a cosine, or cosine squared theta. So that takes care of the numerator. Does that make sense to folks on how we visualize that multiplication here to here? Okay, one thing you can do, if that looks kind of funky in a way, you could write it out this way. Let's take cosine theta. And it's divided by sine theta. And let's just write this in. Sometimes when it's this complicated, this step is not a bad idea. Let's multiply by sine theta times cosine theta. And let's just write out what all these products would actually look like. Same thing in the denominator. This is going to multiply over to here. So it's going to be cosine theta divided by sine theta multiplied by that least common denominator. So times sine theta cosine theta. Then we'll go across plus right here and just do it all over again. Sine theta over cosine theta. Then this, finally, last multiplication multiplies this way. So it's times sine theta times cosine theta. So really, when we visualize it this way, the short of it is, if you multiply the same thing into every single numerator, across numerator and denominator, you have true equality because that's all you're really doing, multiplying by 1. But then upon doing that, here's our reward. Sine theta is canceled there. It cancels here. And cosine theta cancels there. It looks like we're kind of on our way. Now, there's one thing major that we have to spot in order to solve this problem. Feel free to blurt it out the moment you see it. Numerator is so far cosine squared. The denominator is, let's see, cosine times cosine, so cosine squared. Plus, over here will be sine times sine, so sine squared. But at this stage, what would you say the next step must be?
Does it equal 1?
Exactly. This is always a really good thing to recognize the moment it happens, because if we don't recognize that that's equal to exactly 1, we're pretty much stuck. We might think, oh, we just didn't use the right approach. Maybe we made a mistake, but we did not. We're in business here. We have found cosine squared, and we could just say this equals cosine squared theta divided by 1. So therefore, it's cosine squared theta, and that is the right-hand side. It means we did it, folks. That's all we were meant to show on that thing, that the left connects with the right-hand side. Well, any questions at all on getting through that one? Okay, well, this is doing those identities. You have about 3 of them in the homework as well. I'd say 2 of them are about the same as this one, except this is the more difficult one. This was more just to show a different way to prove these kind of ideas where you connect through a common element. Only reason I did this one in class is sometimes that does help out on your homework assignments or even on an exam. But this is going to be more of the routine kind of problems that you're going to see. Any other questions or comments at the moment? Okay, let's save this up. And congratulations, we have completed section 7.1. The moment it's done saving. What we're going into next is section 7.2, and this is where trigonometry starts to get really kind of impressive. The amount of memorization, the amount of identities in trigonometry class are just kind of out of control from a certain point of view. And you can take a look at any moment. Just go to Google and type in trig identities. It's probably going to autocomplete before you put that whole statement. And I'd probably just go to a website or images. And these are the kinds of things that we're getting into. Well, those are the ones we looked at. How about this stuff? This is getting more along the lines. Sum and difference angles, double angle identities, half angle identities. These are the things we're going to be taking a look at in section 7.2, 7.3. I don't expect everyone to memorize these completely. And so part of my goal in this section that we just got through, oh, where is this? Part of my goal in the section that we just got through, once I find my place, is to signify to you that The identities here are in yellow are the ones that you do have to memorize for the course. We're going to pick up a bunch of extra ones, but those are the things I would put in the back of the exam to help support us working through them.
Tangent over the square root of one. Square theta.
Yeah, 'cause that one is just solving for a sine. Yeah, there's some really interesting formulas there. The first ones we're going to look at is these 6 identities. There's a lot to say here, but when you look at these 6 identities, I would say the first question you might have is, how in the heck is any one of these in fact true? It's very unusual for a function to partition in this way. Usually you follow order of operations. You have to do what's inside the parentheses. But if you're restricted to that, calculating cosine pi over 12 is going to be really, really hard. You actually have to break up pi over 12, use the right angle, and make this happen.
I don't know what.
It's law of cosines is almost like this in a certain sense. You'd have idea for law of cosines is you're taking c squared
Sorry,
and extending from this right here. Sorry, question, Hayes?
yeah, I was just like clarifying. All of these gonna be in the like the exam? No, right? The last part that we have learned on Tuesday and Thursday is not gonna be on the exam, this exam.
The exam
it-
only goes to 6.3. Yeah.
Okay. So just like solving the solving the trick and then drawing them, right?
Yeah, the graphing of the functions is 6162, and 63 is the inverse trig functions.
Okay, and the formula sheet will be given, and then you're not gonna do we have to print it out ourselves this time, or it's
No,
gonna
you
be?
do not.
Oh,
yeah.
okay,
Yeah, this is going to be attached as the last page of the exam.
okay, thank you.
Yep, you betcha. Well, one last thing I wanted to take a look at, definitely don't want to keep you too long, is if you're curious how these are derived, here's a really cool proof. This is an ancient proof. Someone did this hundreds and hundreds of years ago. And it kind of went like this. Observe that the distance from here to here is the same as the distance from here to here. People exploited that and calculated the distance function between these two. So from P to Q, that's how you calculate the distance. You would take this coordinate, or P to Q, right? Here's where they calculated it. You would take cosine S minus cosine T and square that difference. Then you would take sine S, sine T, subtract them and square that difference. That's just the ordinary distance formula. But people observed that the distances here to here, where you get the S minus T and the S, is the same as those distances. So you calculate the distance formulas twice, and you have, finally, this distance right here is set equal to that distance. You do a whole bunch of algebra, you obtain that statement right there. Oh, I grabbed the wrong one. You take this right here, set it equal to that one. So there they are. When you square things off, simplify more, and that's the first addition formula. Cosine S minus T equals all of that. Now, you don't have to read this really in depth if you'd like to, but if you're curious on how to derive these identities, that's the proof. It is some weird concoction of geometric figures and distance formulas to give us one. How do you get all the others? Well, you can use angle identities, cofunction identities, all the rest of them emerge from there. We're not going to try to prove all of those. Those are pretty hard. We're going to just show how to work with them directly. So after the exam on Thursday, a week from today, we'll start to show how to calculate weird things like cosine pi over 12 or tangent 23 pi 12ths. You can really do that, but you need this stuff to make it happen. Well, any other questions or comments at the moment, folks, before we call it a night? Okay, I'd say this is a pretty good stopping point for us then. And just a standard offer, if you have any questions while you're studying for your exam 2, don't hesitate to write. I'll be very happy to help out. But have a great night, folks. I'll see you all on Tuesday's class or Tuesday's exam.
Okay, bye.
See you later.
Thank you.
minus is on the top,
Sorry, say again?
plus minus minus is at the top.
Let me see where you're looking. Are you looking at these formulas here? Oh, so, yeah, so what it's saying here is cosine with the plus would turn into a minus. But if you use the minus, it would turn into, or the minus would turn into a plus is what they're saying. What they're trying to do there is they're taking both of these and they're writing it in as just one overall formula. They're writing it as compactly as possible, but unfortunately that makes it also as confusing as possible at the same time. So that short of it is the plus here turns into a minus and the minus turns into a plus. And so that's how they write it as one line.